Hello everyone. Today we are going to do the D and F block elements theory part 5. So let's start our today's topic, that is NCERT chapter 4 D and F block elements theory part 5. Today we are going to cover the NCERT section 4.3.12 to 4.4.1. Let's start. So this is disclaimer. Okay, so today's objective. So after attending this lecture, you will be able to understand the general characteristics of D block elements and the general horizontal and the group trends in them. Also, you will be able to describe the preparation, properties, structures and uses of some important compounds such as K2Cr2O7 and KMnO4. The topics that we are going to be covered today, according to the NCERT, are the first one is the section 4.3 general properties of transition elements, that is D block elements. 4.4.1, that is oxides and oxoanions of metals, in which we talk about potassium dichromate, K2Cr2O7, potassium permanganate, which is KMnO4, and lastly we will conclude with the summary. So let's begin with our first topic, section 4.3 general properties of transition elements, that is D block elements. So the D block elements have various physical properties, and we are covering this from class some theories part of the DNA block. So today what is the part of the general property that we are going to be covered are, so these are the properties that we have been covered, we already had covered in the previous lectures. So today we are going to cover the catalytic properties, the formation of interstitial compounds, alloy formation. Yes, so these are the topics or the general properties of the transition elements that we are going to cover. So let's first of all talk about our section 4.3.12, that is catalytic properties, which is shown by the transition elements. Transition metals and their compounds are well known for their catalytic activity. Okay, so catalytic activity, that means in various types of reactions we use transition metals as a catalyst or transition metal compound. This activity is primarily attributed to two key abilities. Now, why the transition metals show the catalytic activity? It is due to the two major abilities of the transition metals. First, their ability to adopt multiple oxidation states, or you can say that they have this thing, or they have this property to attain various oxidation state, or to be stable in various oxidation state, right? So they have this ability to adopt multiple oxidation states, which is a major reason why they show catalytic activity. Their ability to form complexes, the second ability that is attributed towards the catalytic activity shown by the transition metals, is that they form complexes. Okay, so like coordination complexes, or complexes means in which there is a metal which is basically a transition metal and it is connecting with a different number of ligands, okay, forming a complex. So they have this ability to form complex, which also kind of ability that is going to be attributed towards the catalytic activity of the transition metal. Let's see some examples of transition metal catalyst. First is vanadium oxide, that is V2O5. okay, where the vanadium has +5 oxidation state in the contact process. So vanadium oxide we use as a catalyst in the contact process for sulfuric acid production, H2SO4 production. So the reaction in which we get our product as H2SO4, known as the contact process. In that process, to increase the rate of the reaction, to increase the speed of the reaction, we use the catalyst, which is vanadium oxide. So vanadium is a transition metal, and vanadium oxide is basically the oxide of a transition metal, that is vanadium, right? So we are using a transition metal catalyst in the contact process. This is one example. Then the other example is finally divided iron in Haber's process. Okay, so for the ammonia synthesis, where we get the ammonia in the product, okay, in the synthesis process of the ammonia, we use finely divided iron as a catalyst, and the name of this process is Haber's process. Okay, iron is also a transition metal, so transition metal catalyst is has been used in Haber's process. Third example include the nickel use in the catalytic hydrogenation reaction. Okay. What is the mechanism of catalysis? Okay, so basically solid surface catalyst we are going to talk about. So when transition metal act as catalyst on a solid surface. Okay, solid surface catalyst means that a catalyst having a solid surface on which reactant molecule going to attack and the reaction is going to happen. Okay, so what is the mechanism of catalysis? What is that process through which the catalyst is going to be added up to the reaction, and the reaction is being processed, or the rate of the reaction is being increased? Okay, that's what we are going to see. So when transition metal act as catalyst on a solid surface, they form bonds between the reactant molecules and the atoms of the catalyst surface. So when transition metal will going to act as a catalyst on a solid surface, they will going to form the bonds between the reactant molecule and the atom of the catalyst surface. Okay, why? Due to the interaction between the reactant molecule and the catalyst for the reaction and for the increasing of the rate of the reaction. So first, raw transition metals, that is the 3D series, they utilize their 3D and the 4s electrons for this bonding between the reactant molecules and the atoms of the catalyst surface. Okay, this bonding has two important effects. Now when this bonding is forming between the reactant molecules and the catalyst surface atoms, they are going to show two important effects. So first is increase the concentration of reactants. So reactant molecules, when they are adsorbed onto the catalyst surface, it will increase their local concentration. So reactant molecule concentration on the surface of the catalyst is going to be increased by the interaction between the reactant molecule and the atoms of the catalyst surface. Second effect is that weakens the bond in reacting molecules. So the formation of bonds with catalyst surface weakens the existing bond within the reactant molecules. So when reactant molecules are interacting with the atom present in the surface of the catalyst, the bond which are present among the reactants is going to be weakened. This effectively lowers the activation energy which is required for the reaction to proceed. Okay, activation energy is a minimum amount of energy that is going to be required to initiate a chemical reaction. So this when this interaction between the reactant molecule and the catalyst surface atoms is happening, that means when they are forming the bonds between them, and the reactant molecules bond are going to be weakened, then this is going to be low. This is going to affect the activation energy. So activation energy gets lowers. Okay, and this is a good thing. Okay, if to start a reaction, the energy which you are needed, a minimum energy which you are needed, is going to be lower, that means the reaction will start sudden. Okay, so the reaction will start in a higher rate. Catalysis via change in the oxidation state. So catalysis can also happen via the change in the oxidation state. How? So transition metal ions are particularly effective catalyst because they can readily change their oxidation state. This is the one of the ability of the transition metals which is affecting the catalytic property of the transition element shown by them. So we are saying that the transition metal ions are effectively catalyst because they can readily change their oxidation states, and this allows them to participate in the intermediate steps of the reaction, regenerating their original state by the end. Due to this property of change in their oxidation state, they can even participate in the intermediate steps of a reaction, which is happening between the two steps. Okay, so among the intermediate step of a reaction, catalyst can participate into and also can regenerate their original state by the end of the step. For example, let's say iron catalysis, where iron is in +3 oxidation state. Iron +3 Fe3 plus effectively catalyzes the reaction between the iodide ion and persulfate ions. So I negative and S2OA2 negative ions, when they react with each other, this process is going to be catalyzed by the iron 3 plus ions. So you can see a reaction here, 2I minus plus S2OA2 minus giving us I2 plus 2SO42 minus, right? So this is a reaction happening between the iodide ions and the persulfate ions, and this reaction is catalyzing by the iron 3 plus ions. Okay, so explanation of catalytic action. This is a two-step mechanism. The step 1 include the Fe3 plus oxidized I minus to I2. Okay, so we are talking about the reaction we just have seen between the I minus and persulfate ions. So what happens? This catalytic action shown by the Fe3 plus ions has two major steps. Step mechanism. So step 1 include that iron 3 plus ion is going to oxidize the I minus to I2. Okay, I2 is a iodine molecule in the elementary form. That means its oxidation state is 0 here. So the oxidation state is changing from -1 to 0. That means it is increasing. That means it is a oxidation process. So iron 3 plus is oxidizing I minus to I2 molecule, and in doing so, the iron 3 plus is reduced to iron 2 plus. Also, when iron 3 plus is oxidizing the I negative ions, iodide ions, it is also reducing itself from Fe3 plus to Fe2 plus. So two iron 3 plus ions, when react with two iodide ions, the iron 3 plus ions converts to iron 2 plus ions, and iodide ion converts to or oxidizes to the iodine molecule. The step 2 of this mechanism involve the Fe2 plus ion which we just get. Then they reduce S2OA2 minus to SO42 minus. Okay, so iron 2 plus ion is going to reduce this S2OA2 negative ions to SO42 negative, and in this process the Fe2 positive ion is reoxidized back to iron 3 plus, ready to catalyze another cycle. Okay, so iron 3 plus participate in the reaction between these two ions happening, and what it is going to do, it is going to oxidize the iodide ion to iodine molecule and also going to reduce itself to the 3 plus to 2 plus. Now when the ions which we get in the form of iron 2 plus, this is going to reduce the S2O8, the other ion, S2OA2 negative, the other reactant, to SO42 negative, and in this process the iron 2 positive is again going to oxidize back to iron 3 positive. That means whatever we are using our catalyst in the initial step, that we are using iron 3 plus. So after the end of the step, we are regenerating the initial catalyst that we are doing, even after having some changes in between the reaction or in between the mechanism steps, right? So iron 3 plus has been changed to iron 2 plus, then again iron 2 plus reoxidize itself back to iron 3 plus, and ready to catalyze the another cycle. So iron 2 plus when reacts with S2OA2 negative ions, it was going to convert itself to 2Fe3 plus, that means oxidize itself to 2Fe3 plus, and also reduce S2OA2 negative ions to 2SO42 negative. This cycle shows how transition metal, that is iron here, facilitates the reaction by undergoing a change in oxidation state and then regenerating itself. This is what it is happening. It is participating in the reaction, the iron, and facilitating the reaction to get the correct product, and also undergoing a change in oxidation state and then regenerating itself also. Okay, let's move to our next section, that is 4.3.13, that is formation of interstitial compounds. Okay, so let's talk about the interstitial compounds. Interstitial compounds are formed when small atoms like hydrogen, carbon, and nitrogen get trapped within the vacant spaces, or you can say intersites of crystal lattices of the metal. Okay, so we are talking about the crystal lattice of metal, of the transition metals. Okay, so in the starting we have seen that transition metal exists in different crystal lattices like BCC, body centered cubic, CCP, cubic closed packing, HCP, hexagonal closed packing, right? So what we are saying that the vacant spaces or the intersites which are forming in these crystal lattices of metals, in those vacant spaces some small atoms like hydrogen, carbon, or nitrogen trapped. Okay, in these vacant spaces these small atoms is going to be trapped and they are going to form this interstitial compounds. They are usually non-stoichiometric, that means their formula don't represents the simple whole number ratio. For example, VH0.56, because the quantity that are going to be trapped in the vacant spaces, it may be or may not be in the whole number ratio, right? In a whole, like in a proper crystal lattice of metal, if you see, it may or may not be in a proper whole number ratio. So they are usually non-stoichiometric, for example VH0.56, the vanadium hydride. They are neither typically ionic or nor covalent in their bonding character. If you talk about the bonding character, they neither ionic nor covalent, that means they don't even like share their electrons between the atoms, and not even like give away their electrons completely to form the ionic bond. Okay, due to the nature of their composition, atoms residing in the interstitial sites, they are specifically referred to as interstitial compounds, and this is the reason that due to the nature of their composition, that in the vacant spaces they are like small atoms are going to be filled or going to be trapped, right? In the interstitial sites of the crystal lattice of the metals, the small atoms are going to be trapped, and due to this nature of their composition, they are specifically referred to as the interstitial compounds. Some examples of interstitial compounds are TIC, MN4N, Fe3H, okay, hydride, okay, VH0.56, TiH 1.7, etc. So these are the examples. You can see some are non-stoichiometric, that means the formula is not in simple whole number ratio, right? So let's see some key characteristics of interstitial compounds. These compounds possess distinct physical and chemical properties like high melting points. So they typically have high melting points. They means interstitial compounds have high melting points higher than those of the pure metals from which they are formed. Okay, so pure metals means basically interstitial compounds we have said that formed by the like occupancy of the vacant spaces by the smaller atoms, right? So The interstitial compounds show higher melting points than those of pure metals from which they form. Okay. This indicates strong bonding within the lattice. Why they show higher melting points? Because within the lattice, they are having stronger bonding, even between the atoms that are being filled in the vacant spaces and between the transition metal present in the crystal lattice. Extreme hardness. Also, the another physical property shown by the interstitial compound is that they have extreme hardness. So they are very hard. Some borides, which are interstitial compounds formed with the boron, are so hard that they approach diamond in the hard. Diamond is the hardmost element, right? So some borides which are formed, some interstitial compound which are formed with the boron, they are so hard that they approach the diamond in their hardness. The third property is metallic conductivity retention. So despite the incorporation of non-metal atoms, they retain their metallic conductivity. Okay, so as we are talking about transition metal lattices, so their atoms are still of metal, right? But in their vacant spaces, we have been filled non-metal atoms. So still, if after the incorporation of non-metal atom, they retain their metallic conductivity. This is because metallic bonding network largely remains intact in the crystal lattice of the metal. The chemical inertness they have shown, so they are generally chemically inert, the interstitial compounds. That means they are highly resistant to the chemical attack or the reaction. They doesn't react with anyone. They don't show any reaction or any chemical attack on it. Okay, so they are generally chemically inert. This enhanced stability is due to the strong bonds which are forming between the atoms. Let's talk about alloys. Our next subsection 4.3.14, that is alloy formation. So alloys, which is, you can also say, blends of different metals. An alloy is a mixture of metals formed by combining their components. So how the alloy form? It formed by mixing different metals by combining their components. What is the key concept here? Alloys can be homogeneous solid solutions where the atoms of one metal are randomly distributed amongst the atoms of the another. Formation of alloys. So crucial condition is that such alloys typically form when metallic radii of the component atoms are within approximately 15% of each other. What does that mean? That one metal atom, so such alloys form when one metal's atom replaces another's in a crystal lattice, and when the metallic radii of component atoms are 15% of each other. Okay, so why we choose transition metals for the alloy formation? So transition metals readily form alloys due to their similar atomic radii. They show similar atomic radii, which helps in the formation of the alloy. Okay, why? Because size similarity allows for atoms to substitute into the lattice structure without the significant distortion leading to a stable alloy. Right? If the size is going to be like same or similar, the stability of alloy will going to be good. Okay, so it will not affect any significant distortion due to the similarity in the atomic size, due to which the alloy will be stable, which is formed by those transition metal. The other shared characteristics are variable oxidation state shown by the transition metal atoms, also the metallic bonding shown by them. Okay, and these are the properties that why we are considering transition metals for the alloy formation. Properties and importance of transition metal alloys. First thing is enhanced properties. So alloys formed by the transition metals are generally hard. They are often possess high melting points. Okay, so alloys formed by transition metal. Okay, the alloys which are formed by the transition metal, they are generally considered as hard. Okay, due to the, you know, the strong bonds formed between the atoms, and also they are possesses high melting points. Their melting point is also high, again due to the same reason, due to the strong bonding. Ferrous alloys, that is iron based alloys, these are most well known and industrially significant alloy. Common alloying elements are chromium, vanadium, tungsten, molybdenum, manganese. So these are the like common elements that are going to used in the alloying formation. Okay, in the, like, they are called alloying elements, we are calling them. Okay, they are used extensively in the production of various types of steel, because steel is an alloy, and also stainless steel. Okay, so these are the properties that first of all, that alloy formed which are formed by the transition metals have enhanced properties, like they are hard, they are having high melting points, and some iron alloys, that is iron based alloys, are formed which are well known, and also the industrially significant alloys, that means they are going to be used industrially. And some common alloying elements include chromium, vanadium, tungsten, molybdenum, and manganese, and they are used they are used extensively in the production of steel, various types of steel, and stainless steel. Alloys with the known transition elements. So, transition metals also form important alloys with non-transition metals. Okay, so alloys can also be formed with non-transition metal. So transition metal can form important alloys with non-transition metals. So examples of industrial importance. First one is brass. Like industrially, the examples which the examples which of the alloys which are going to be used, or which are used in the industrial process, or industrially in a broad way. First alloy is brass, which is an alloy of copper. Copper is a transition metal, and zinc. Zinc is a non-transition metal. We consider zinc as a non-transition metal due to its electronic configuration. Bronze, the another alloy, which is an alloy of copper, which is a transition metal, and tin, which is a non-transition metal. Now let's talk about the another subsection, oxides and oxoanions of metals, the 4.4.1. So let's talk about oxides of transition metals. So in this, first let's cover the formation of oxides. Transition metal oxides are generally formed by the reaction of metals with the oxygen at higher temperature. So at higher temperature, when metal reacts with oxygen, the metal oxides, transition metal oxides, generally formed. The important note is that all the transition metals except scandium form MO type oxides, where M is metal, O is oxygen. So except scandium, all transition metals form MO type oxides, and these MO oxides are typically ionic in nature. Highest oxidation states in the oxides. So the highest oxidation number which are observed in the oxides of transition metals, they are generally coincides with their group number. Like if some element is present in group, let's say 7, okay, so the highest oxidation number which is observed in that element oxide is going to be +7, okay, shown by that element. This trend is observed from scandium 2O3. Scandium in group 3, oxidation number in Se2O3 is +3. Okay, scandium is having +3 oxidation state in scandium oxide, and scandium is present in group 3. So this trend is observed in this compound of scandium up to manganese. So this trend is observed. Which trend? That the highest oxidation number which is observed in oxide of transition metal generally coincides with their group number. So if you see, the group number of scandium is 3, and also this oxide found by the scandium has oxidation number of +3 shown by the scandium in this oxide, up to manganese, this manganese oxide, where manganese is showing +7 oxidation state, and manganese is also belongs to group 7. Okay. The exception or limitation related to this, that beyond the group 7, that is beyond the manganese oxide, for example iron, the higher oxides, then Fe2O3. Now iron in group 8, and the oxidation number shown by it in this oxide is +3. So higher oxides, which is shown by iron, that is Fe2O3, are not known. Okay, so the exception or limitation include that beyond the group 7, after the group 7, the higher oxides than Fe2O3 are not known. They are not known. Now, stabilization by the oxocations. So, besides simple oxides, transition metals can form stable oxocations, the ions which contains both metal and oxygen. Okay, so besides the simple oxides which are shown by the transition metals, transition metal can form stable oxocations, which includes the ions of metal and oxygen both. For example, vanadium in +5 is stabilized as vanadium O2 plus, right? So this in this oxocation, vanadium +5 is stabilized. Okay, it is stable. So it is a stable oxocation formed by the transition metal vanadium in its highest oxidation state, that is +5. Now vanadium +4 is stabilized by the formation of this stable oxocation VO2 positive. Similarly, Ti +4, so titanium in its highest oxidation state +4 is stabilized as TiO2 positive, this oxocation. What are the nature of oxides? So we talk about ionic character versus the covalent character and acidity. So the key trend observed is that as the oxidation number of a metal in its oxide, okay, in its oxide form means the metal oxide form, the oxides formed by these transition metal, and in those oxides the oxidation number shown by metal increases, and as this oxidation number increases, the ionic character of the oxide is going to be decreases, and covalent character is going to be increases, because they are both like opposite. If ionic character is decreasing for oxide, covalent character is going to be increase if the oxidation number of a metal in the oxide is increasing. What are the consequences of increased covalency? The higher oxidation states. So Mn2O7, which is like manganese oxide, where the manganese in its highest oxidation state, that is +7. Now this is a covalent green oil. Okay. Now even the chromium oxide, where chromium in +6 oxidation number, and vanadium oxide, where vanadium is in +5 oxidation number, they have low melting points indicating significant covalent character. Okay, so they have low melting points. Why? Because they have their significant significant covalent character shown by them. Predominant acidic character. So in the higher oxides, where metal is in a high oxidation state, acidic character is predominant factor. So Mn2O7, where manganese in highest oxidation state +7, reacts with the water to form a strong acid, HMnO4, name permanganic acid. CrO3, where Cr is in +6 oxidation state, reacts with water to form H2CrO4, known as chromic acid, and H2Cr2O7, known as dichromic acid. Okay, so in the higher oxides where metal are already in their highest oxidation state, acidic character is going to be predominant. That means those oxides, when reacts with water, they are going to form strong acids. Okay, amphoteric nature and acidity trend, and some examples. So V2O5 is amphoteric in nature, meaning it can act both as an acid and a base. Although it is mainly acidic, we consider it as an acidic compound, but it can act as both acid and base. That's why we are calling it as an amphoteric compound. Okay, so V2O5 is amphoteric. It can form VO4 negative salts, which act as an acid, and VO2 positive salts, which act as a base. And this is the reason due to which we are calling this vanadium oxide, where vanadium is a transition metal, and this compound or this oxide formed by this vanadium is amphoteric. Gradual change in the vanadium oxides. So there is a clear trend in the nature of vanadium oxides, the oxide shown by vanadium, with increasing oxidation state. So V2O3, where vanadium is in +3 oxidation state, is basic. V2O4, where vanadium is in +4 oxidation number, is less basic. It dissolves in the acids to give VO2 positive salts. Okay, so it is comparatively less basic than V2O3. And V2O5, where vanadium is in highest oxidation state +5, is amphoteric. That means it will going to be react with both alkalis to give the VO4 negative salt and acid to give VO2 positive. Chromium oxides. Now let's talk about chromium oxides. So chromium oxide like CrO, where Cr, that is chromium, is in +2 oxidation number, which is a basic oxide. Cr2O3, where chromium is in +3 oxidation number, it is an amphoteric oxide. Okay, let's talk about the oxide of the metal potassium, potassium dichromate, K2Cr2O7. Now, what is the importance of this compound and what is its uses? So potassium dichromate is a very important chemical. It is used extensively in the leather industry. It is act as powerful oxidant for the preparation of many azo compounds. Okay, so in the preparation of azo compounds, we use potassium dichromate as an oxidant. It acts as a powerful oxidant. Now, the preparation of dichromate include, that is, we are going to see the industrial method. Dichromates are generally prepared from chromates. So chromates are obtained by fusion of chromite ore, that is FeCr2O4, with the sodium or potassium carbonate in the presence of air. So chromates, from the chromates we form dichromates, and chromates are obtained by the fusion of chromite ore, that is FeCr2O4, with the sodium or potassium carbonate. When the chromite ore, that is this FeCr2O4, is going to react with sodium or the potassium carbonate in presence of air, we are going to obtain the chromates. So the step 1 in the preparation of dichromate include roasting of chromite ore, where the formation of sodium chromate happens. So reaction include 2 FeCr2O4 plus 8 Na2CO3 plus 7 O2. Okay, these three compounds react with each other in the presence of air, right? So oxygen. So these two compounds react with each other in the presence of air and form 8 Na2CrO4 plus 2 Fe2O3 plus 8 CO2, 8 molecules of carbon dioxide. Okay. Now, this produces a yellow solution of sodium chromate, Na2CrO4. This Na2CrO4 we are getting in the product. This is a yellow color solution. The step 2 in the preparation of the dichromate include the conversion of chromate to dichromate, that is acidification process. So the yellow sodium chromate solution which we got is filtered and then acidified with the sulfuric acid. The reaction involves 2Na2CrO4 plus 2 protons gives us Na2Cr2O7 plus 2Na plus water molecule, and this yields orange sodium dichromate, that is Na2Cr2O7.2H2O, which can be crystallized. So yellow color solution of sodium chromate changed to the orange sodium dichromate, which can be crystallized. Okay, so this we talk about the two steps. The first includes the formation of sodium chromate, and the second includes the acidification process, which could include the conversion of chromate to a dichromate. Okay, and formation of a orange sodium dichromate solution. The step 3 includes the preparation of potassium dichromate from sodium dichromate. Okay, we just got sodium dichromate in the step 2. So how can you prepare potassium dichromate? Let's see. So sodium dichromate is more soluble than the potassium dichromate if you compare. Therefore, the potassium dichromate is prepared by treating the solution of sodium dichromate with potassium chloride. Okay, so when you just got the sodium dichromate and when you react it with the potassium chloride KCl, you will going to get the potassium dichromate. Reaction includes sodium chromate react with the potassium chloride. Okay, sodium dichromate react with the potassium chlorides, form potassium dichromate plus 2 NaCl. The orange color crystals of potassium dichromate, that is K2Cr2O7, crystallizes out in this reaction due to its lower solubility. Right, so potassium dichromate is lesser soluble, so that's why we crystallize the potassium dichromate out from the solution of the sodium dichromate due to its lower solubility. Okay, and this is a orange color crystals of potassium dichromate. Now let's talk about the interconversion of chromate and dichromate ions. Chromate, that is CrO4 negative, and dichromates, that is Cr2O7 negative, are interconvertible in the aqueous solutions. So chromate and dichromate are interconvertible. This interconversion is dependent on the solution's pH in which they are present. If pH is less than 7, okay, in the acidic medium we are talking about, the chromate, that is 2CrO4 negative, which is yellow color solution, reacts with or attach the two protons into itself and form a orange, that is dichromate solution, Cr2O7 negative, and release water molecule. Meanwhile, in the alkaline medium where the pH is more than the 7, the orange color solution of dichromate Cr2O7 negative reacts with two hydroxyl ions, forms a yellow color solution of chromate ions plus water molecules. The key point to remember is that the oxidation state of chromium in both the chromate and the dichromate, that is CrO4 negative and Cr2O7 negative ions, is same, that is +6. Okay, so chromium has same oxidation state, same oxidation number in both chromate and dichromate ions. Now, structures of the chromate and dichromate ion. So chromate ion has a tetrahedral geometry. So you can see this image where the chromium is at the center and it is attached to 4 number of oxygens, whole 2 negative charge on it because it is a chromate ion. So the geometry is a tetrahedral geometry. Okay, so at each 4 corners one oxygen is present. Meanwhile, dichromate ion Cr2O7 negative consists of 2 tetrahedra sharing of 1 corner. There is also a chromium oxygen chromium bond present in the dichromate ion structure. The chromium oxygen chromium bond angle is 126 degrees. This is a structure of dichromate ion where 2 chromium are joined with 1 oxygen. So chromium oxygen chromium bond is existing. The bond angle of the chromium oxygen chromium is 126 degree, and each chromium is attached with 3 other oxygens, okay, and whole 2 negative. This is a dichromate ion. The bond length is also different. The chromium oxygen chromium bond length of chromium oxygen bond is 179 picometers. Meanwhile, the oxygen and the chromium bond length is 163 picometer other than the chromium oxygen chromium bond, right? So you can see two tetrahedra, that is this structure and this structure, are sharing one corner by this bond chromium oxygen chromium formed. Let's see the oxidizing properties of dichromates. Both the sodium and potassium dichromates are strong oxidizing agents. Meanwhile, their solubility are different. They are strong oxidizing agents. Sodium dichromate more soluble in water, and it is extensively used as oxidizing agent in the organic chemistry. Oxidizing agent means it oxidizes, thus gets reduced itself. Potassium dichromate, on the other hand, is used as a primary standard in volumetric analysis. So they have their different uses. Okay, like sodium dichromate is used as oxidizing agent, and potassium dichromate is used as a primary standard in the volumetric analysis. Oxidizing action in acidic solution. Half reaction showing reduction of dichromate. So Cr2O7 2 negative, the dichromate ion reacts with 14 protons and 6 electrons, converting to chromium 3 positive plus 7 water molecules. Okay, the E0 for this is positive 1.33 volt. Okay, so here we are showing the reduction of dichromate where chromium is in plus 6 oxidation state or oxidation number, converting to the chromium in plus 3 oxidation number, the reduction of dichromate. And this indicates that the acidified potassium dichromate can oxidize a variety of substances by getting reduced from chromium plus 6 to chromium plus 3. So potassium, or you can say acidified, because we are talking about H positive. We are reacting the dichromate ions with H positive ions. So acidified potassium dichromate oxidized variety of substances by the reduction from chromium 6 positive to chromium 3 positive. Specific oxidation reactions by acidified potassium dichromate. So the oxidation reactions specifically shown by acidified potassium dichromate are: first one is iodide to iodine. So half reaction include the 6 iodide ions converts to iodine molecule plus releasing 6 number of electrons. Second reaction oxidation reaction is sulfides conversion to the sulfur. So half reaction involve the 3H2S converts to 3S, okay, sulfur plus 6. It will also produce 6 number of protons and 6 number of electrons. Third specific oxidation reaction is 10 from plus 2 to 10 and plus 10 from plus 2 to 10 plus 4. The half reaction include 3SN2 plus converting to 3 SN4 plus 6 electrons. So 10 from 2 plus is converting to 10 in 4 plus also releasing 6 number of electrons. The fourth reaction is iron from iron plus 2 salts to iron and plus 3 salts. A half reaction include the 6 iron 2 positive converting to 6 iron 3 positive, releasing 6 number of electrons. So these are the examples some specific oxidation reactions which are shown by the acidified potassium dichromate. Okay, the iodides to iodine, sulfides to sulfur, 10 plus 2 to 10 plus 4, iron plus 2 salts to iron plus 3 salts. The example of full ionic equation or dichromate oxidizing the iron 2 plus ion is by adding the half reaction for the dichromate reduction and iron plus 2 oxidation. Okay, so iron plus 2 oxidation and the dichromate reduction, when you add these two half reactions, you will get this major reaction, that is Cr2O7 2 negative, the dichromate ion reacting with 14 protons plus 6 Fe2 plus ions and giving us 2 chromium 3 plus 6 Fe3 plus 7 number of water molecules. So we are getting from dichromium to chromium in the plus 3, from +6 to +3, and also the iron from +2 to +3. Now let's talk about our another oxide of the transition element potassium, that transition element manganese, that is potassium permanganate, KMnO4. Okay, so preparation of potassium permanganate. Let's first of all see the preparation. So first we can prepare the potassium permanganate from pyrolusite ore, which is of MnO2. The laboratory or the general method include: step 1, fusion with the alkali and oxidizing agent. Okay, we fuse it with an alkali, the first group elements, and oxidizing agent. So MnO2 is fused. So we are talking about the preparation of potassium permanganate from the pyrolusite ore. Okay, formula includes MnO2, where the oxide of the manganese is found in the form of MnO2. The general or the laboratory method include the step 1, where we fuse this MnO2 with the alkali and oxidizing agent. So when MnO2 is fused with an alkali metal hydroxide like KOH and an oxidizing agent like KNO3 in presence of oxygen. So we are reacting the MnO2 with alkali metal hydroxide and oxidizing agent in the presence of oxygen. The reaction includes 2 MnO2 reacting with 4 KOH, the alkali metal hydroxide, plus oxygen, giving us 2 K2MnO4 plus 2 water molecules. This produces dark green potassium manganate, that is K2MnO4. This K2MnO4 which we are getting in this process, in this reaction, in the step 1. So this is a dark green colored potassium manganate which we are getting. The step 2 include the disproportionation of, so manganate ion, that is MnO4 2 negative, disproportionates in a neutral or acidic solution to give the permanganate, that is MnO4 negative ions. Okay, so MnO4 negative, MnO4 2 negative manganate ion disproportionates to give permanganate MnO4 negative. So the reaction includes 3 MnO4 2 negative, the manganate ion, reacting or disproportionating in acidic solution, so adding 4 protons, giving us a permanganate ion, that is 2 MnO4 negative plus MnO2 plus 2 molecules of water. The commercial preparation of potassium permanganate. So we have seen the laboratory method of the potassium permanganate, right, which we have seen in the second step, from manganate to permanganate conversion. Now if you talk about the commercial preparation of this compound, it involves the alkaline oxidative fusion of manganese oxide, so MnO2 fused with potassium hydroxide and oxidized with air or KNO3 and converts to MnO4 2 negative, that is a manganate ion. Now this manganate ion, after electrolytic oxidation in alkaline solution of it is converting to the permanganate ion, that is MnO4 negative. Okay, so this is a alkaline oxidative fusion method or a commercial preparation of potassium permanganate. This is followed the alkaline oxidative fusion of MnO2 followed by electrolytic oxidation of manganate plus 4 to permanganate, as we have seen in this process. Okay, so these two processes are involved. Laboratory method. So from manganese 2 positive ions, how can you prepare the potassium permanganate? Let's discuss the laboratory method. Manganese in the +2 salt are oxidized by peroxodisulfate, that is S2OA2 negative, to permanganate. Okay, so manganese +2 ion salt oxidized by this peroxodisulfate to the permanganate. The reaction includes 2 Mn2 positive plus 5 S2OA2 negative plus 8 water molecules, converting it to MnO4 2 negative permanganate plus 10 SO4 2 negative plus producing 6 number of protons. This is how you can get permanganate from the manganate by the from the manganese 2 positive ions by the oxidation of them by using the peroxo disulfide ions. Now let's talk about some physical properties of the potassium permanganate. So firstly, it forms a dark purple, or you can say almost black crystals. It is isostructural with KCl4, KClO4. The solubility, if you talk about the solubility, it is not very soluble in the water, or 6.4 gram per 100 gram of water it can be soluble at 293 Kelvin temperature. Thermal decomposition, so it decomposes upon heating at 513 Kelvin. The reaction, it shows that 2K-MnO4 reacts converts to K2MnO4 plus MnO2 plus oxygen. Now the magnetic properties of it, so it exhibits intense color. It is diamagnetic due to absence of unpaired electrons in the MnO4 negative permanganate ion. In the permanganate ion, there is not any presence of the unpaired electrons, due to which it is act as diamagnetic. It shows weak temperature dependent paramagnetism. Okay, so its magnetic properties is going to be weakly dependent upon the temperature. Structure of its ions. So both the manganate ion and the permanganate ion are tetrahedral in the structure. Pi bonding occurs. Why? Due to the overlap of oxygen p orbitals with manganese d orbitals. And due to these overlap of the orbitals between oxygen and manganese, the pi bonding will occur. Now, what is the distinction in the magnetic behavior? So, green manganate, that is MnO4 2 negative, is a paramagnetic because it has only one unpaired electron. So, you can see this is tetrahedral manganate ion, MnO4 2 negative, green in the color, right? Mn connecting with 4 number of oxygen, 2 is O negative and 2 other is the double bond O. Okay, this is a paramagnetic, there is only one unpaired electron. The another is the purple permanganate, which is MnO4 negative. The magnetic behavior it shows is diamagnetic because it has no unpaired electrons. The structure involves this Mn double bond O, double bond O, double bond O, and single bond O negative. This is a tetrahedral permanganate ion, which is purple in color. It has no unpaired electrons, so that's why it is diamagnetic. Some oxidizing properties of potassium permanganate. It is acidified permanganate solution that are strong oxidizing agents. The reduction of permanganate depends upon the solution's pH. Acidified permanganate solution oxidizes the oxalates to carbon dioxides, iron plus 2 to iron plus 3, nitrites to nitrates, and iodides to free iodine. Half reactions of reductants are, so this COO negative, the 5 molecule of this converts to 10 CO2 plus 10 electron. 5 Fe2 plus converts to 5 Fe3 plus 5 electron. So oxalate converting to carbon dioxide, iron 2 plus converting to iron 3 plus. Similarly, nitrites here, after reacting with water molecule, converting to nitrates, and iodide ion is converting to free iodine molecules, releasing 10 number of electrons. These are the half reactions of this reductants. H positive effect on the permanganate reduction. Reduction to the manganate, that is in strongly alkaline medium. So MnO4 negative plus electrons give us MnO4 2 negative. The E naught is positive 0.56. Now reduction to manganese dioxide in the neutral or faintly alkaline medium, where MnO4 negative reacts with the protons plus electrons and giving us MnO2 and water molecule. E naught include positive 1.69 value. Third is reduction to manganese plus 2 ion in the acidic medium. So MnO4 negative reacts with 8 protons and 5 electrons, converts to Mn2 positive plus 4H2O, the E naught include the value of 1.52 volt. Okay, so how the presence of H positive is affecting the permanganate reduction, this we are seeing in various medium. The key factor in this that the hydrogen ion concentration, that is H positive ion concentration, play a crucial role in influencing the reaction and the product formed in each of the reaction you have seen. Kinetics consideration, that although the redox potential are important, kinetics of reaction also matter. So example is that permanganate at H positive concentration equals to 1 should oxidize the water, but reaction is very slow. So unless Mn2 positive ions are present or the temperature is raised. Okay, so either autocatalysis happen or the temperature should be raised for this oxidation process. Okay, so kinetics is going to be a factor which you have to consider along with the redox potentials. Now, important oxidizing reactions of the potassium manganate, permanganate. First of all, in the acid solutions, the permanganate reduced to Mn2 plus. Oxidation of iodides to iodine is one of the reactions include. So 10 iodide ion plus 2 MnO4 negative plus 16 H positive. So we are getting 2 Mn2 positive from them, 8 water molecules and 5 iodine molecules. So in the acid solutions, the permanganate is converting to Mn2 positive, and also the oxidation of iodide to iodine is happening. Second is oxidation of iron 2 plus to iron 3 plus. So iron 2 plus, which is green in color, reacts with MnO4 minus plus 8H plus, converts to Mn2 plus, 4 water molecule and 5 Fe3 plus. So iron 2 plus converts to iron 3 plus, and also the permanganate is reduced to Mn2 plus. Third is oxidation of oxalate ion or oxalic acid to carbon dioxide at a particular temperature, where the 5 Cr2O42 negative reacting with MnO4 negative and 16 protons, giving us the Mn2 positive, 8 water molecules and 10 carbon dioxide molecules. So oxalate ion converting to the carbon dioxide, also the permanganate is reducing to the Mn2 positive. Fourth, oxidation of hydrogen sulfide to sulfur. So 5s2 negative plus 2 MnO4 minus plus 16 protons reacting with each other, forming 2 Mn2 plus 8 water molecules plus 5 sulfur atoms, right? So sulfide converting to sulfur and permanganate reduced to Mn2 positive. Oxidation of sulfurous acid or sulfide to the sulfate or sulfuric acid. So 5SO3 2 minus plus 2 MnO4 negative plus 6H plus, giving us 2 Mn2 plus 3 water molecules plus 5 SO4 2 minus ions. So sulfurous or sulfite converting to sulfuric acid or sulfate, and also the permanganate is reducing to the Mn2 positive. Fifth is oxidation of nitrite to the nitrate. When nitrite reacts with MnO4 minus and protons, it converts to Mn2 positive, permanganate reduced to Mn2 positive, and nitrite converts to nitrate and also release 3 number of water molecules. So these are the oxidizing reactions in the acid solutions shown by the KMnO4. Second is in neutral or faintly alkaline solution, where permanganate is reduced to MnO2. It includes the oxidation of iodide to iodate. This is a notable reaction. So where MnO4 minus reacts with water molecule and the iodide ions converts to iodate, IO3 negative, and permanganate is reduced to MnO2. Second is oxidation of thiosulfate to the sulfate, which is almost quantitatively. Now here the 8 MnO4 negative reacting with 3 S2O32 negative plus water molecules and converting the permanganate or reduction of permanganate is happening to MnO2, And also the thiosulfate is converting to the sulfate ions, SO4 2-, releasing 2 hydroxyl ions. Third is oxidation of manganese salt to MnO2. So the presence of zinc sulfate or zinc oxide catalyzes this oxidation of manganese salt to MnO2. So MnO4 minus plus 3Mn2 plus water molecules gives us 5 MnO2 plus 4 number of protons, and this oxidation is catalyzed by zinc sulfate or zinc oxide presence. Important note on titrations. So permanganate titrations are unsatisfactory in presence of hydrochloric acid, because hydrochloric acid can also be oxidized to chlorine by permanganate, leading to inaccurate result. And what are the uses of potassium permanganate? So beyond the analytical chemistry, it is a favorite oxidant in preparative organic chemistry. In the organic chemistry, we use it as an oxidant. Its strong oxidizing power is utilized for bleaching of wool, cotton, silk, and other textile fibers. It is also used for decolorization of the oils. Okay. So let's see the summary of the content that we have covered today, that is NCERT section 4.3.12 to 4.4.1. First of all, we have talked about the catalytic properties shown by the transition metals due to their ability to adopt multiple oxidation states and their ability of formation of complexes. And the solid surface catalysis works by adsorbing of the reactant, which weakens the bond among the reactant molecules and increase the bonding between the atom of the surface of catalyst and the reactant molecules. Transition metal ion catalyzed by cycling through different oxidation states. And through this they can participate in the intermediate step and regenerate themselves. Interstitial compounds was the second topic we have covered, where we have seen that they form when small non-metal atoms like hydrogen, carbon, or nitrogen get trapped in the vacant metal lattices of transition metals and its compounds, leading to non-stoichiometric and unique materials. They exhibit high melting points, extreme hardness, metallic conductivity, and the chemical inertness also. Then we talked about the alloy formation. So alloys are the metal mixtures we have seen, which are often homogeneous, formed when the component metal radii are almost within 15% similar. Transition metals form alloys like stainless steel due to the similar atomic radii, which results in harder materials with higher melting points. Also, they form important alloys with non-transition metal. Like transition metal form alloys with non-transition metal, like example is brass, which is a alloy of copper and zinc, and bronze, which is a alloy of copper and tin. Then we talked about oxides and the oxoanions of metals. Transition metal form oxides, typically the ionic MO types. Highest oxidation states in the oxides generally match with the group number of the element, like manganese in +7 up to manganese in +7, beyond which higher oxides are not known. Oxides with higher oxidation state become more covalent and acidic. For example, Mn2O7, which is a strong acid. Now, acidity increase with oxidation number, which shows a trend from basic to amphoteric to the acidic character. For example, vanadium and chromium oxides, which follow this trend. Next, we talk about our compound potassium dichromate. This is a powerful oxidant which we use industrially, like in leather industry and also in labs. It's manufactured from chromite ore and then converted to the sodium chromate to sodium dichromate, and finally less soluble potassium dichromate, which is a useful thing. Like its solubility is it's less soluble. Potassium dichromate is a useful thing. Its solubility, less soluble thing, is a useful thing in obtaining it. Chromate and dichromate interconvert based on the pH of solution, and they both have +6 chromium present in it. Dichromate is a strong oxidizing agent which reduces chromium plus 6 to chromium 3 plus in the acidic solutions. Next, we talk about our another compound, that is potassium permanganate, that is KMnO4. Potassium permanganate is a powerful purple oxidant. This is prepared from MnO2 via manganate, either by fusion or by disproportionation in the lab, or the electrolyte oxidation which we use in the commercial production. Its reduction products and the oxidizing power strongly depend upon the pH. So like if acidic, it is going to be give us Mn2 positive. If the solution is neutral or alkaline, it is going to give us MnO2. It oxidizes various substances, but it is not suitable for the titration with the HCl because it is also going to oxidize this also. It uses include in the organic synthesis like bleaching and in the oil decolorization. Okay, so thank you so much. That's all for today's chemistry session. Thank you.